Hey, this is Presh Talwalkar. Here's a multiple part interview question. You have wooden blocks numbered 1, 2, and 3, and another set of wooden blocks also numbered 1, 2, and 3. You need to arrange the 6 blocks in a row according to the following rule. You need to place the 2 blocks that are numbered 1 with exactly 1 block between them. You also need to place the 2 blocks that are numbered 2 with exactly 2 blocks between them. Finally, you need to place the 2 blocks that are numbered 3 with exactly 3 blocks between them. So that's the first challenge. How can you arrange these 6 blocks in a row according to that rule? Now let's get to the next challenge. Let's add 2 blocks that are numbered 4. You also need the 2 blocks that are numbered 4 to be placed with exactly 4 blocks between them. So the second challenge, can you arrange these 8 blocks in a row according to the same rule? Now let's go one more step. Let's add 2 blocks that are numbered 5. You also need the 2 blocks that are numbered 5 to be placed with exactly 5 blocks between them. Now before you solve this challenge, you actually need to prove the following, that it's impossible to make an arrangement of these 10 blocks according to that rule. So that's the interview question. By way of history, this problem originated in 1958 when C. Dudley Langford was noticing his child play with colored number blocks, and he just happened to notice that for certain arrangements, there was 1 block between the 1s, 2 blocks between the 2s, and 3 blocks between the 3s. This became generalized into the following mathematical problem. Imagine you have the numbers 1, 1, 2, 2, and so on up to n. You need to arrange the numbers in a permutation such that there is 1 digit between the 1s, 2 digits between the 2s, and so on up to n digits between the n's. Such a sequence of numbers is known as a Langford pairing. So the first question, for which values of n is this impossible? In other words, what are the necessary conditions so there is a solution for n? The second part, for which values of n is there a solution? What is the sufficient condition so that there is a solution for n? I will end the video with an open or unsolved question. When there is a solution, how many solutions are there? And it's an interesting thing that this is unsolved for n greater than 30. So with this setup in mind, pause the video if you'd like to give this problem a try. And when you're ready, keep watching to learn how to solve this problem. Let's start by solving the blocks that are numbered 1, 2, and 3. I really hope you've attempted this problem because it's a very fun puzzle to solve. So here's how I approached it. I thought about starting with the 2 blocks that are numbered 3. Because you need to place them with 3 blocks apart, there are limited positions to try. So one possibility is putting them in positions 2 and 6. There are 3 blocks between them. We can also shift it over 1 spot, so we have positions 1 and 5. But that's it. These are the only positions you could try. Because you need to have 3 blocks between them, there aren't too many places you can put them. Now, let's start with the 2 blocks that are numbered 2. You can't put it in positions 2 and 5 because position 5 is already taken. So let's try positions 3 and 6. There are 2 blocks between them. That only leaves 2 spaces for the 2 blocks numbered 1, and this will be positions that are correct. There's exactly 1 block between them. So we've come across a solution. 3, 1, 2, 1, 3, 2. Now, you might have come up with another solution. So imagine reading the numbers from left to right. 3, 1, 2, 1, 3, 2. Well, you could of course read the numbers from right to left. 2, 3, 1, 2, 1, 3. So whenever you have a solution, you could reverse the numbers and you would come up with another solution. So 2, 3, 1, 2, 1, 3 will of course also be a solution. So this will have the blocks spaced in exactly the right positions. So you could say these are two different solutions, but mathematicians like to say this is actually one solution. So this is one solution up to reversal of the numbers. We'll keep that in mind as we go through the solutions of the other puzzles. So now let's solve the problem with the numbers 1, 2, 3, and 4. As before, let's start out with the largest pair of numbers, which is 4. So there aren't too many places to try for the 4, so let's just try in the first block and the sixth block. So there are 4 blocks between them. Now, we can just experiment and try the 2 blocks numbered 3. We can put them over here, so there are 3 blocks between them. In order to leave spaces for the 2 blocks numbered 1, there's only one spot we can put the 2 blocks that are numbered 2, so we try that. And finally, we have 2 spots remaining, and the 2 blocks numbered 1 will exactly fit here. So we have a solution: 4, 1, 3, 1, 2, 4, 3, 2. Again, this is one solution up to reversal. To illustrate that, let's imagine we take the same numbers and we read them going from the end. So this will be 2, 3, 4, 2, 1, 3, 1, 4. This is another solution, but really we'll just say the first is the unique solution up to reversal of the numbers. Now, if we have the blocks numbered 1 to 5, we need to prove that it's impossible to come up with a solution. So rather than trying all the different possibilities, we're going to systematically attack this problem. So let's say we have 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. So we need to place these into 10 positions. So let's number each position as 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. What can we say about these positions? Well, consider the 2 blocks that are numbered 1. If one block is at position A, the left block, then the other block will need to have one space between it, so it will be at position A plus 2. So the block at A plus 1 is exactly between them. Consider the 2 blocks that are numbered 2. If the left block is at position B, then we need to have B plus 1 and B plus 2, so then the right block will be at B plus 3. When we have 3 and 3, it will be at positions C and C plus 4. 4 and 4 will be at positions D and D plus 5. And 5 and 5 will be at positions E and E plus 6. So, how does this help us? If we have a solution, then the positions of these 10 blocks, A plus 2, and so on, will exactly need to be equal to the positions 1 to 10. So let's do some analysis on this. If this is the case, then the sum of the numbers on the left needs to exactly be the sum of the numbers on the right. So what's the sum of the numbers on the left? Well, we have 2 copies of A, 2 copies of B, 2 copies of C, 2 copies of D, and 2 copies of E. So we have 2A plus 2B plus 2C plus 2D plus 2E, and then we need to add 2, 3, 4, 5, and 6 for the offsets. Now what's the sum on the right-hand side? It's the sum of the numbers going from 1 to 10. So there's the famous formula, n multiplied by n plus 1 all over 2. So here n is equal to 10, and we have 10 multiplied by 11 all over 2. So on the left-hand side, we can factor out the 2 for all of the variables. We have 2 multiplied by the sum of A, B, C, D, and E. Then we need to add the numbers 2, 3, 4, 5, and 6. Notice this is the sum of the numbers going from 1 to 6 minus 1. So we will write this as 6 times 7 divided by 2 minus 1. Then the right-hand side is equal to 55. So we'll simplify the left-hand side. The sum of those numbers is equal to 20. And then we'll subtract 20 from both sides. So we have 2 multiplied by the sum of the variables is equal to 35. Now let's analyze this equation. We have 2 multiplied by the sum of these variables is equal to 35. But each of these variables needs to be an integer, so the sum of the integers is an integer, and we have 2 times an integer is equal to 35. But 2 times an integer needs to be an even number, and 35 is an odd number. So this is impossible. there is no way that we can arrange the numbers, because that would lead to the contradiction that 2 times an integer is equal to 35. Therefore, no solution exists. We can now generalize this approach to find the necessary condition for a solution. So let's say we have blocks that are numbered 1, 1 up to nn. So if we have 2 blocks that are numbered k, we can put their positions as the left block as ak and the right block as ak plus k plus 1. This will mean there are k blocks between the 2 blocks numbered k. So if a solution exists, we can consider the positions of the blocks. It'll be a1, then a1 plus 1, and this will go up to the last block of an and an plus n plus 1. This needs to exactly be equal to the position of the blocks, which will be the numbers from 1 to 2n. So we will sum the left-hand side, and that needs to be equal to the sum on the right-hand side. For the sum on the left-hand side, we have 2 of each variable a1 up to an. So it'll be 2 multiplied by the sum of these variables, plus we have the sum of the numbers going from 2 to n plus 1 for the offsets. This will be equal to the sum of the numbers going from 1 to 2n, which will be 2n multiplied by 2n plus 1 all over 2. Let's simplify this equation. We need to calculate the sum of the numbers going from 2 to n plus 1. So we can do the formula for the sum of the numbers from 1 to n plus 1 and then subtract 1. So this will be n plus 1 multiplied by n plus 2 all over 2 minus 1. Let's multiply both sides of the equation by 2. We have 4 multiplied by the sum of the variables a1 to an plus n plus 1 multiplied by n plus 2 minus 2 is equal to 2n multiplied by 2n plus 1. Let's expand the binomials and then collect like terms. So we have 4 multiplied by the sum of a1 to an is equal to 3n squared minus n. Let's analyze this equation. We'll divide both sides of the equation by 4, so we have the sum of a1 to an is equal to 3n squared minus n all over 4. Since the left-hand side is the sum of integers, it will be an integer. So the necessary condition is the right-hand side also needs to be an integer. That is, 3n squared minus n must be divisible by 4. So when does that happen? It'll be convenient to think modulo 4. So there are 4 possibilities to consider. N is equivalent to 0 mod 4, 1 mod 4, 2 mod 4, or 3 mod 4. So we'll work out each case. In the first case, 3 times 0 squared minus 0 is equivalent to 0 mod 4. Then we have 3 multiplied by 1 squared minus 1. That's equivalent to 2 mod 4. That's not evenly divisible by 4. That's a remainder of 2. If n is equivalent to 2 mod 4, we have 3 times 2 squared minus 2. That's equivalent to 10, which is equivalent to 2 mod 4. That's not evenly divisible by 4. Finally, if n is equivalent to 3 mod 4, we have 3 multiplied by 3 squared minus 3, which is equivalent to 24, which is equivalent to 0 mod 4. So we can see in the 2 middle cases, if n is equivalent to 1 or 2 mod 4, we will end up with 2 mod 4, which is not evenly divisible by 4. So to summarize this, if n is equivalent to 1 or 2 mod 4, it is impossible. There is no solution. So we just worked out n is equal to 5. That is equivalent to 1 mod 4. We showed there was no solution. The same thing will be true where n is equal to 6, because that will be equivalent to 2 mod 4. On the other hand, if n is equivalent to 0 or 3 mod 4, then it's possible that a solution may exist. At this point, we can't say for sure that a solution exists. In order to do that, we proceed to the next part, which is showing a construction that a Langford pairing always exists. It's going to be quite complicated, but let me just give a flavor of the proof. This was first shown in 1959 by Roy Davies, and I came across wonderful write-ups on the website of Susam Pal and Vamshi Jandhyala. So we get started by defining a number x. It'll be equal to n over 4 if n is a multiple of 4, or it will be n plus 1 divided by 4 if n is equivalent to 3 mod 4. We can succinctly summarize these two cases by saying x is equal to the ceiling of n divided by 4. So you take n divided by 4 and you round up. That'll summarize these two cases. Once we have this number x, we can construct a sequence. We define four numbers a, b, c, and d as 2x minus 1, 4x minus 2, 4x minus 1, and 4x. We define a sequence p to be all the odd numbers in ascending order in the interval 1 to a minus 1 inclusive. Define another sequence q to be all the even numbers in the interval 2 to a minus 1 inclusive. Define r to be the odd numbers in the interval a plus 2 to b minus 1 inclusive. And finally, define s to be the even numbers in the interval a plus 1 to b minus 1 inclusive. Finally, define r of a sequence to be the reversal of the sequence s. Then define the following sequence. We want the reversal of s, the reversal of p, b, p, c, s, d, the reversal of r, the reversal of q, b, a, q, c, r, a, d. This is for n is equivalent to 0 mod 4. We have another sequence if n is equivalent to 3 mod 4. This will be the reversal of s, the reversal of p, b, p, c, s, a, the reversal of r, the reversal of q, b, a, q, c, r. So the two sequences are very similar, but there will be just some minor differences. The first sequence has this number d, which is not there in the second sequence, and in the second sequence, a replaces d. So let's just try one example to see how this works. Let's take n is equal to 12, which is a multiple of 4. It's equivalent to 0 mod 4. So x will be equal to n divided by 4, which is equal to 3. We can then define a, b, c, and d to be equal to 5, 10, 11, and 12. We now come up with the sequences. P will be equal to 1, 3, Q will be equal to 2, 4, R is equal to 7, 9, and S is equal to 6, 8. So we go through this sequence of numbers and we get the following: 8, 6, 3, 1, 10, 1, 3, 11, 6, 8, 12, 9, 7, 4, 2, 10, 5, 2, 4, 11, 7, 9, 5, 12. And amazingly, this is a Langford pairing. You can actually check that the two numbers 1 will have one spot between them, and so on. All the way up to the two numbers 12 will have 12 numbers between them. So this is an absolutely amazing construction. Now, to be completely rigorous, you have to check that every single digit in this construction actually does follow the rule of the Langford pairing. It's not too hard to do, so I'll leave that for the excited reader to actually work out for themselves, or you can check the proof that's linked in the video description. So now I just want to go over one more point. So how many solutions are there for a particular n? So for n is equal to 7, we know that a solution exists, but in fact, 26 solutions are possible up to reversal. And here are all of them on the screen. So all of these sequences are Langford pairings. So it's not just that if you have a solution, you're going to have exactly one. You could have multiple solutions. So when n is equal to 7, there are multiple sequences that work. Now, in general, this is a very difficult problem to work out. If you have n and you need to know the number of solutions, well, of course, for some cases, we know that it's 0, but in other cases, it's going to be a very large number. So these are the numbers that have been worked out. So the largest worked out number is n is equal to 28. It's a very large number. We know that 29 and 30 will be 0. Now, what about 31? Nobody knows the answer to this. This is unsolved. So these large cases actually can take weeks and months to work out with various computers actually cranking through the numbers. And it's very difficult because you're dealing with possible computation errors. This is an absolutely fascinating problem. A mathematician was just looking at his child play with wooden blocks. He came up with an interesting puzzle, and it's actually led to a problem that's still unsolved to this day. Wow. Thanks for making us one of the best communities on YouTube. See you next episode of Mind Your Decisions, where we solve the world's problems, one video at a time.